So we've seen how to train a regression model to predict a numeric value. Now it's time to look at another kind of supervised learning, classification. Classification is a technique that we can use to predict which class or category something belongs to. The simplest variant of this is binary classification, where we predict whether an entity belongs to one of two classes, and often that's used to determine if something is true or false about the entity. For example, suppose Rosie keeps records of which days she made a profit and which days she didn't. And she has the features of each day, including the temperature, rainfall, and the number of flyers she distributed. We can train a machine learning model that can be applied to the daily features and give the result 1 for days that are profitable and 0 for days that aren't. Or more generally, a binary classifier is a function that can be applied to features x to produce a y value of 1 or 0. Now the function won't actually calculate an absolute value of 1 or 0. It will calculate a value between 1 and 0. And we'll use a threshold value to decide whether the result should be counted as a 1 or a 0. When you use the model to predict values, the resulting value is classed as a 1 or 0 depending on which side of the threshold it falls. Because classification is a supervised learning technique, we withhold some of our test data to validate the model using known labels. Cases where the model predicts a 1 for a test observation that actually has a label of 1 are considered true positives. Similarly, cases where the model predicts 0 and the actual label is 0, these are true negative. If the model predicts 1 but the actual label is 0, well, that's a false positive. And if the model predicts 0 but the actual label is 1, that's a false negative. The choice of threshold determines how predictions are assigned to classes. In some cases, a predicted value may be very close to the threshold but still misclassified. You can move the threshold to control how the predicted values are classified. In some scenarios, it might be better to have more false positives but reduce the number of false negatives, and in other scenarios the opposite might be better. Either way, the number of true positives, true negatives, and false negatives produced by your model is crucial in evaluating its effectiveness. The counts of these are often shown as what's called a confusion matrix, and this provides the basis for calculating performance metrics for a classifier. The simplest metric is accuracy, which is just the number of correctly classified cases divided by the total number of cases. In this example, there are 5 true positives and 4 true negatives, and there are also 2 false positives and no false negatives. So that gives us 9 correct predictions out of a total of 11, which is an accuracy of 0.82 or 82%. Now that might seem like a really good result, but perhaps surprisingly, accuracy actually isn't all that useful as a measure of models' performance. Suppose, for example, that only 3% of days are profitable. I could predict a model that simply always predicts 0, and it would be 97% accurate. But that's completely useless for identifying which days will be profitable. A more useful metric might be the fraction of cases classified as positive that are actually positive. This metric is known as precision. In other words, out of all of the cases that we classified as positives, which ones are in fact positive. In this case, there are 5 true positives and 2 false positives. So our precision is 5 out of 7, which is 0.71. So 71% of cases identified as positive really are profitable days, and 29% are misclassified. In some situations, we might want a metric that's sensitive to the fraction of positive cases we correctly identify, and we call this recall. It's calculated as the number of true positives divided by the combined true positives and false negatives. In other words, what fraction of positive cases are correctly identified. In this case, there are 5 true positives and no false negatives. So our recall is 5 out of 5, which is of course 1 or 100%. So in this case, we're correctly identifying all of the profitable days. Now recall actually has another name. Sometimes it's known as the true positive rate. And there's an equivalent rate for false positives compared to the actual number of negatives. In this case, we have 2 false positives and 4 true negatives. So our false positive rate is 2 out of 6, which is 0.33. Now you may remember that the metrics we've got here are based on a threshold of around 0.3. And we can plot the true positive rate against the false positive rate for the threshold like this. If we move the threshold back to 0.5, our true positive rate becomes 4 out of 5, or 0.8, and the false positive rate is now 1 out of 6, or 0.167, which we can plot here. Moving the threshold further to, say, 0.7 gives us a true positive rate of 2 out of 5, or 0.4, and a false positive rate of 0 out of 6, or 0. If we plotted this for every possible threshold rate, we'd end up with a curved line like this, and it's known as the receiver operating characteristic, or ROC chart. Now the area under this curve, or AUC, is an indication of how well the model predicts. Generally, you want to see a large AUC, with the curve staying as close to the top left corner of the chart. A perfect classifier would go straight up the left-hand side and then along the top, giving an AUC of 1. You can compare this curve with a diagonal line, which represents how well this model would perform if you simply made a 50-50 guess, or an AUC of 0.5. In this case, the model has an AUC of around 0.9, so it definitely outperforms guessing.